So in this class, we started looking at springs. So the first thing we were doing, we were checking out different springs, feeling them, and just visually telling what's different and physically what's different about them. And students noticed that it took a lot more force to pull some springs than others. The springs that were harder to pull on were much thicker and heavier. So what we then did was we did some data analysis. We found out how much force was required to stretch the springs different lengths. So we were plotting force and spring elongation x, how far the spring stretches or compresses. And we took some data and they found that there was a linear relationship between the two. If we put force on the y-axis and x, spring elongation on the x, we got a pretty linear relationship. So if we were asking, how would you describe the relationship between force and elongation? You could say that it's a linear or a direct relationship. As force goes up, so does spring elongation. We then found the slope, and we found that the slope had units of newtons per meter. And when asked what does the slope represent, students said things like the springiness of the spring or the stiffness of the spring. And what it actually represents is something we call in physics the spring constant. Which we're going to abbreviate with a lowercase k. So the stiffer the spring, the bigger the spring constant. And it has units of newtons per meter. This relationship that students discovered is referred to as Hooke's law. So Hooke's law is F equals kx. So force, the force that you're using to pull or compress the spring, measured in newtons. The spring constant, k. Measured in newtons per meter. And x, which is the spring elongation or compression. Measured in meters. So x is the distance the spring is stretched or compressed from equilibrium in meters. So just to draw a little picture of what that looks like. So if this is my spring and its regular length, and this is my spring up here when it's compressed, and this down here is when it's stretched out, the value of x is how far it stretches from equilibrium. So for the first spring, it's actually compressed from equilibrium, so this would be our value for x. For the second spring, since it's stretched from equilibrium, this would be our value for x. Okay, it has nothing to do with the original length of the spring. It's only how far it moves from equilibrium. So the next part, we're given a slope of a graph, or we have to find the slope of a graph with force on the y-axis and stretch distance of a spring on the x-axis. So to find the slope, we're going to do rise over run. So our rise here is about 10.5 newtons, and our run is about 0.16 meters, for a slope of 66 newtons per meter, which is also our k value. For the next question here, we want to find how far a spring stretches. So we're given the mass of the spring, or excuse me, a mass hung from the spring, which is 0.25 kilograms. You have to convert that from grams. and you're given the K value of 150 newtons per meter. So the first thing it asks us to do is find the weight pulling on the spring, or the force pulling on the spring. So that's equal to mg, which is equal to 0.25 kilograms times 9.8 meters per second squared. And working through that one, you should get about 2.45 newtons is the force pulling on the spring. So to find out how far this spring stretches, we're going to use our F equals kx, where F is 2.45 newtons, K is 150 newtons per meter, and X is our unknown. Throwing that in our calculator, we have 2.45 divided by 150, and we get about 0.016 meters, about 1.6 centimeters is our X value, how far the spring was stretched. For this next one here, we're given the spring constant, read it carefully, that's the spring constant, not the force, K, of 68 newtons per meter. And the force here is 12 newtons. So if we use F equals kx again, the force is 12. Our K value is 68. I'm just leaving the units out now, just for space. So to solve for x here, we're going to divide both sides by 68. So we have 12 divided by 68. We get about 0.18 meters, or about 18 centimeters. For the next one, I like this next one because it doesn't give you much in the wording. You have to look at the picture. So realize here that the X value for this one is 0.1 meters, okay? 0.1 meters is our X value, okay, because that's how far the spring stretched. The force pulling on the spring is 35 meters, or newtons rather. So using F equals kx, the force is 35 newtons, X is our unknown, or excuse me, K is our unknown, and X is 0.1 meters. So we have 350 newtons per meter.